In this video, I will find a Taylor series representation for the square root of x at a specific center and use that to approximate the square root of 4.2. Now the reason why I'm doing a square root of x as my function is I want to show that not all functions make good Maclaurin series, meaning you can't do Taylor series at centers of 0 for all prompts. For instance, let's look at the square root of x. If I do begin with finding f of x being the square root of x, plug in my center of 0, there's not an issue. 0 gets divided by 0 factorial, which is 0 divided by 1. It gets multiplied by 1. I get 0 as my starting amount, which will be basically my 0th order prediction, which makes sense. The issue becomes when I find the derivative of f. I will come up with 1 over 2 radical x. Now if I plug 0 into that, I will be dividing by 0. And essentially what this is telling me is I'm getting a vertical slope, and that's just not possible. And it doesn't make a good prediction. So 0 is off the table. So what I need to do now is I need to think about this and find a center that I know and is also close to 4.2. I got it. Let's reset and set our center to 4, because I know that if I actually take 4 and plug it into f of x, my starting term will be 2. 2 gets divided by 0 factorial, and then I will multiply that by 1, and lo and behold, that's my first term. And so let's start showing the approximation here. Now as I move across to the first degree, or first order, and I get that derivative of 1 over 2 radical x, I can plug 4 into that where I couldn't plug 0 before. 1 over 2 times radical 4 is 1 over 2 times 2, which is 1/4, which is 0.25. And then I'll divide that by 1 factorial, and I'll come up with x minus 4. Notice down here, now, the way I write my linear approximation, which is the first order Taylor series, is 2 plus 0.25, or 1/4, times the quantity x minus 4. Now I never actually stated what degree my Taylor series will go to for my approximation. I want to see enough to get the feel of it, but let's not go ridiculous either. Let's just make it a third degree. So I'm going to need to now find the second derivative of f, which works out to be negative 1 over 4x radical x. And if we want to rewrite the denominator, that would just simply be 4x to the 3/2. I plug 4 into there, and I'm getting a very interesting decimal, negative 0.03125. I still got to divide that by 2 factorial to get that coefficient. Well, the good news is I do have an option here where I can just start looking at the final result. Ooh, significantly better numbers, negative 1/64. That will get multiplied by x minus 4 quantity squared. So when we come down here, we got to remember that's negative 1/64. So this is my second degree polynomial. I wanted to actually find a third degree polynomial for my approximation, so let's go find the third derivative, which is 3 over 8x squared radical x. I believe that's 3 over the denominator 8x to the 5/2. We plug 4 into that, we get this decimal. Now remember, this decimal is not actually 1 over 512. That actually is that number divided by 3 factorial, which then simplifies as 1 over 512. And we will then multiply it to the quantity of x minus 4, quantity raised to the third. Remember, it's x minus 4 throughout the process because our center is 4. So now that we have this third degree polynomial, which is represented by this cubic graph in blue, let's go ahead and approximate the square root of 4.2. We'll come over here and we'll set x equal to 4.2. And as we do so, please note how well the blue curve is actually predicting around 4.2 because we chose a very good center. And in fact, our prediction should be 2.04939, which, oh my goodness, that is a really tiny error. The question is how do I actually get that value? So thanks to the magic of editing, I've popped up my stylus, and I'm going to plug in my value of 4.2 for x into my third degree Taylor series polynomial. I know that the square root of 4 is 2, and I know that 0.25, which is coming from this column right here, is also 1/4. And then I'll subtract 4.2 by 4, and there's my linear approximation. And then if I want to make it a quadratic polynomial, I will subtract 1/64 times 4.2 minus 4 squared. And then to complete my third degree polynomial, I will add 1 over 512, and multiply that by 4.2 minus 4 to the third. And this is going to produce the result that's right here. Of course, wherever you saw 4.2 minus 4, you could have felt free to put 0.2 into all these spots here and here and here, and maybe have to type less into the calculator. But that's up to you. But in all the cases, a third degree polynomial will do a very nice job predicting for values close to 4. Now, if I want to predict something for that was close to 9, maybe 8.5 or 9.3, then I think I should be using a center of 9. And you can kind of get the idea how this works. If you're watching this video, you may notice that the audio has significantly changed. You may even think that the screen has changed a little bit. You're not wrong. Yes, I've gone back and edited this video a couple years later when I first did the last one. And to make it even more strange, I'm not even doing that drastically different of a problem. I'm doing the approximation of square root of 5 instead of the approximation of square root of 4.2. And we're even using the same center of 4. Why? Because later on when I do Lagrange's error bound, I'm going to use this as one of my examples. So it'd be helpful if we had this to kind of go back to in reference. So let's not waste any time. Let's go do our third order Taylor series. And we'll put in x is 5 into the function f of x equals the square root of x. And, well, that's also x to the 1/2. Again, we're choosing a equaling 4 because we're taking the square root of 4 because we know what the square root of 4 is. The square root of 4 happens to be 2. And so when I plug that into here, that will make a great center. It's close to square root of 5, and I can easily figure that out. 2 will then get divided by my nth factorial, which in this case is 0. And that means I'm going to multiply that by 5 minus 4, and that quantity will be raised to the 0. Now, some cool things about this particular example. First, 5 minus 4 is always going to be 1. So it's going to be a little easier to work with than the last one because 1 to the 0, 1 to the first, 1 to the second, it's always going to be 1. The second thing is you're not having to deal with my handwriting. You can read this. So let's just simplify this. 2 divided by 0 factorial, well, is 2. And that's kind of how we started before. So let's continue on by taking the derivative of f of a, which in this case is 1/2 times a raised to the negative 1/2, or simply 1 over 2 radical a. Again, nothing's changed. We're even going to plug in the same 4 and come up with 1/4. We're even going to take that 1/4 and divide it by 1 factorial. The only difference is now we're going to multiply it by 1 to the first, which means it's just 1, which means it's just 1/4 divided by 1, which means it's just 1/4. That's a little different than before. So we're going to continue on. F double prime of a equals negative 1/4 a to the negative 3/2. Or you can see it on the right, what it simplifies to with the radical in the denominator. Either way, you're going to plug 4 into it. And you're going to still come up with negative 1 over 32, and it's going to get divided by 2 factorial. But being multiplied by 1 squared means it's simply negative 1/64. And finally, f triple prime of a being 3/8 times a to the negative 5/2, being 4 plugged in, leads to 3 over 256, but don't forget to divide that by 3 factorial, or in this case 6, so that then you can actually write plus 3 over 1536. And so our approximation is 2.236328125, when in actuality it's 2.236067977. And so as I come back to a familiar screen over here, you'll see how our polynomial, right now raised to the third order, is this nice cubic, and it's doing a pretty good approximation, at least right here, for our square root of 5, which is right there. And so the error, this number minus this number, is 0.000260145. Again, this is what the actual error is because I happen to know what the square root of 5 is. What I want to do later on is, maybe I don't know exactly what the square root of 5 is, but I would like to find what is the maximum error I'm actually off with my blue function compared to where I should be on the red graph, and that's how we're going to use Lagrange's error bound. And that will come in a later lesson, and that's why I did this one right now.